So let's look at trying to exploit target 6 on another chip. I've shown how to do it on the x86-64 and also the RISC-V. I also have an ARM64 machine, and we can try hacking it there. This is running on a new Mac M1. So let's take a look at check password as usual. And so we see that it is storing a pair of registers, x29 and x30, to the stack pointer. Stack pointer minus 48, so I guess it's it just keeps track in its head where the top of its stack pointer is, and then it's okay. Then it's going to move move the stack pointer into x29 so that that'll be passed to the next routine if it calls it. And then I think it's storing a 0 into in offset 44 from the stack pointer, and that is probably that variable. That's the number of tries you've had. It's what has been in. It was what it looked like in the RISC-64. And let's jump down here to validate password, and we see actually right before validate password. So this is the place where it's storing that that value in the exclamation point, the hex 21. If it's valid, and it would store a 78, hex 78, and X if it's invalid. And if we look right above that, what it's doing is it's getting the address 41200, but then it's adding 68 to it, giving us 412068. So that I would think is the address of where this 21 is stored, because X0 gets 412000, adds 68 to it to get 412068. It loads into the working register 1 the constant 21 hex and stores that in the location pointed to by X0. So I'm pretty sure that that's where that flag is that we use with the call to open lock. So the other things we need to know when we've been hacking this program is we go back and look at the call to prompt, and let's see, X0 X0 is the first argument. X1 should be the second argument, and X2 has the third. Okay, so X2 has gotten X0. X0 is the stack pointer plus 18. So stack pointer plus 18, and then if I scroll back down to validate password, right below that, it's where it adds 1 to the counter of how many times you've done this, and that is stack pointer plus 44. Oh, that was 18. I'm sorry, this is in decimal. This is going to drive me crazy. And the previous time, the previous call, it was in hex. So I don't know why GDB does that. So that is probably close to all the information we would need. Let's just jump back a second and look at main and see where the call to open lock is. And that is at 4006 AC. So let's make a note of that. So we already know, based on experience with this hacking this program, where to look for the buffer that we're going to overflow, where the counter is of how many times you've done the password, so that we make sure we don't overwrite that with 0, but instead overwrite it with something large enough that it'll immediately drop out of the password loop, return to the code that we've stuck on the stack, and execute it. And we now know where we need to return. So let me try writing a little bit of ARM assembly code that would exploit that. So we're going to edit t6 arm.s, and I think My ARM is not that great, but I think if I do load x0 with a constant, there's some weird things we have to do. It's very difficult to get big numbers into ARM registers like immediate, and this is one way to do it. It'll turn out a little ugly, I think, but it'll be workable. And then what we want to do is move into working register 0, 1, that constant, just like we saw in the code. So this, that should be move. Okay. And then we're going to store that byte, W1, into the location pointed to by X0. So that's the 412068 that we saw earlier. And then we want to load X0 with the address we want to jump to, which is 4006 AC. That's still right up here on the screen, you can see. And then we want to jump branch to register X0. So that jumps to that register. So that should be it. So let's assemble it. T6arm.o, T6arm.s, and obj dump -d T6arm.o. Okay, so we see oh, okay. So when I did that load R with the equal sign, what that actually does is generate some stuff that's relative to the execution. So it's saying pull the value from the area of memory that's 18 past where I am now, and so it's down here. So our code will actually contain these constants. But oh boy, so all right, let's jump over here real quick and take a look at check password. Gonna put a breakpoint there, and I'm gonna run, and then I'm going to just do the things that are gonna set up the stack. Okay, now this is what the stack looks like. So the stack pointer, I'll hide this again for a moment. Stack pointer is pointing to 2D0, and remember that the buffer that we're passing to prompt is at stack pointer plus 18 hex. So that would be plus 1, D0 plus 1 is E0, plus 8 is 2E8. So this is where the buffer starts. And it's going to go in memory for at least 2 of these, because it's, I think the other thing should appear soon. The other one, the variable was at 44, stack plus 44, and so this is stack plus 8, 16, 24, 32, 40, 1, 2, 3, 4. So this right here is where that variable goes. So we started here at E8, and the variable is here. So that's only 2.5 words. We have to have a non-zero value there. That's 3 words. Okay. We have an interesting challenge here. This is something that ARM does that's interesting. So what we encounter here is notice that the return address is the first is at the top of the stack frame, not at the bottom of the stack frame. And so the buffer that we're writing to, that's here at E8 and goes somewhere down here, is below the return address. And so what we would have to do to exploit this is really overwrite the return address of the function that called check password. But unfortunately, the way this is set up, as an example, this is not a good example, because main is calling check password directly, and main will signal whether or not the lock was opened, and then this simulator program will terminate. So the problem is that by the time we could overwrite this, in a live processor, what we would want to do is overwrite this area here at FFFF300 and FFF308, and this at 308 we would presumably have our return address. I may be a little off here. That doesn't look quite right. But the problem is the return address we want to write would be earlier in memory than where the buffer overflow is working. So it turns out that just because of the way ARM does things and the way this simple program was structured and the way it interacts with the simulator, the buffer overflow won't work. So instead, I created a target 6 ARM, and the difference is, so when we look at check password now, it just saves its stack pointer and return address and then calls check password impl. So this is an extra layer of indirection. So now if we break at check password impl and then continue and then go here and look at the stack, so now instead of the stack starting at 2D0 where it was before, it's starting at 2C0. And it's already pushed its return address, and the return address would go to 4006E4, which is just past the call up here to check password impl. And so now the other thing is, so there's all this space here that the stack pointer uses, and let's see, 48 is 30. So C0 plus 1, 2, 3. F0 then is where the stack frame is for check password. And so you see it has its old stack pointer and its return address. And so now, because this is the return address to go back to main, we can exploit this, because we can have our buffer overflow write this stuff. And the other problem that we would have had this happened on the RISC-V, we would have had an issue. Look at the size of this assembly code: 1, 2, 3, 4, 5 words, and we would be trying to stick it in at D8, 1, 2, 3, 4, 5. It would, just the code itself would overwrite the area we would want to exploit. So we have to be a little more careful. But I think we have a solution. It's just gonna take a little work. What we're gonna do is we're gonna overflow the buffer here, starting at 2D8, and we're gonna just fill in zeros here, because we don't care. We're actually not going to the buffer. This time the buffer, the good part of the buffer that is not going to contain the code. It's going to be way down here. So what we're going to do is just write out zeros, and somewhere along here we're going to have to put in like a hex 10 or something to set up that failed password counter. And then when we get down to here, we're going to overwrite this stack pointer. We don't really need to, I think, overwrite this, but we do want to overwrite this return address, and we're going to send it to right below here in the stack. So we're going to send it to FFFFF300, and that's where this code is going to start executing. So let's look at T6 ARM. Let's make a T6 ARM.txt. Oh, let me do this. Let me copy these assembly instructions and just I can VI and paste them in. All right, so this is the code that we want, and I'm gonna, again, just like I had to do with the ARM6, I'm going to reverse all these bytes. There's probably some, I could do some VI foo to do it automatically, but I'm just going to do it manually. So C0, 00, 00, 58, 21, 04, 80, 52. So that's the first two instructions. And then 01, 00, 00, 39. And again, I'm doing these in blocks of 8 because that'll match up with the memory and it'll make it easier for me to keep track of what's going on. And I'm doing A0, 00, 00, 58, so that I just did this one here. And now I'm going to do 00, 00, 1F, D6, 00, 00, 00. Yeah. I did something wrong there. Oh no, I didn't. I just, yeah. I did this. These 4 zeros are this one here, and so now I'm going to do 68, 20, 41, 00, and then the next, the 1C here is 00, and then AC 06, 40, 00, and then 00, 0, 0. Okay, so this is the code. Now this code is going to go here at FFFFF300, and the return address is going to go right before it. So I want the return, I want what appears right before that to be 00F3 FFFFFFF 0000. So that's the return address, and so instead of 4006A4, it's going to go to FFFFF300. And then the line before that is actually the same. That's the stack pointer, and we can just let it be the same. Now, let's see. I think if I worked it out right, this 15 here is where that counter is, and so that should be 00000000 10. So a hex 10, which is 16, to update that counter. And then this is where the buffer is. The data we're entering. We don't care about it. We're just going to put in zeros. So this is at this first line here is what would be at 2D8. So there's zeros for these first two, and zeros, and then a hex 10 to update that counter, and that's here. And then the return, the old stack pointer, the return address, and then our exploit code. So let's see if that works. And I'm going to just, again, pop out of VI because I had some bad... I've noticed Vim is now updates the system clipboard when you delete stuff, and it's been driving me crazy. Okay, so this should be what we want to paste in here. So I am going to... No, I was going to be really risky and just do it, but let's just watch it. So I'm going to set a breakpoint here. Then I'm going to hit continue, make sure the X is there for hex input, and paste this in, hit enter, and we hit tab to go back over here. And now I'm going to step. So I expect validate password will return false, because what are the odds that the password was all zeros? Oops, enter. Okay, and it's equal to 0, so it's going to go here where it's incrementing that flag. And let's look. So this was where we put the flag over here at 2E. That would be what? A2EC. We should see this 10 here flip to an 11 right after this instruction. Oop, if I hit enter. Yeah, good. So we did that right. So we're going to keep going, and it's not less than or equal to 0. So now this is where it's going to load the address of that 412068 and it's storing a 78, and we want to put a 21 there. It stores it, and now it's loading back out the old stack pointer and instruction pointer and doing a return. So now we are at the call to check password impl. And so now when we do this, when I do next here, the program counter is now at FF300, which is down here where our code starts. So I can't step through that because the disassembler doesn't disassemble the stuff on the stack. So the only thing I can do is hit C and hope I did it. The unlock succeeded. So one of the things that you run into sometimes with, especially with the ARM processors, is because ARM processors are RISC machines, just like the RISC-V. The reduced instruction set sometimes means that you have to execute more instructions than you do with a complex instruction set. And if the stack frame you're exploiting is smaller than the instructions that you want to put in there, you have to do some creative things about keeping the stack structured the way in order to let things flow, and sticking your code somewhere down in the stack where you can jump to it and execute it. And it can be a little tricky, but we were able to do it with this one. Although again, I had to make a custom version of the target because it wouldn't have worked with the original.